Hello everyone. Today I will be talking to you about the three-phase induction motor. What is induction motor? Induction motor is an alternating current motor that works depending on the electromagnetic induction phenomenon. Like any other motor, the induction motor is an electromechanical device that converts the input electrical power to a mechanical output power. An induction motor can be a three-phase or a single-phase power supplied. The induction motor has so many advantages, like its high efficiency and its high power factor, also its cheap price, and of course that it requires a low maintenance. Induction motor, also known as the asynchronous motor, because the rotation speed of the rotor is always less than the synchronous speed. Induction motors are classified depending on its rotor type. If the rotor type is an squirrel cage rotor, the induction motor is a squirrel cage induction motor. If the rotor type is a slip ring rotor, the induction motor is a slip ring induction motor. So here we can see the equivalent circuit of an induction motor. As you can see, it's very similar to the transformer equivalent circuit. And if you think about it, the transformer transfer the energy from the left side of the primary to the right side of the secondary, and the same thing happens at the motor. As we have at the left side we have the stator, and at the right side we have the rotor. But the only difference here is that at the transformer the voltage changes only, but in the induction motor both voltage and frequency change. So here we can see the components of the equivalent circuit of an induction motor. Here at the left side of the stator we can see R1 and X1, which are the resistance of the stator and the leakage reactance of the stator. And of course we have the core losses reactance RC and XM, the magnetizing reactance for the air gap. At the right side here to the rotor we can see X2, the reactance of the stator, and R2 over slip, which is the resistance of the rotor. And here we have E1 and E2, which both are the induced EMF at both sides. Now we are going to talk about the components of the induction motor. There are mainly two main parts, and they are the rotor and the stator. The stator is the stationary part of the induction motor. It contains the permanent magnet that creates the rotating magnetic field that interacts with the rotor. Now in the middle we see the rotor. The rotor is the central part or the central component of the induction motor. It's constructed of aluminium and copper. As we mentioned before, there are two types of the rotors. There are the squirrel cage type and there is the slip ring type. The rotor is connected to the mechanical load through the shaft. As we see, the core is laminated into thin parts to reduce the effects of the eddy current losses. The three-phase power supply is given to the induction motor through the stator. We see here the part that extends out of the induction motor. This part we call shaft. The shaft is connected directly to the rotor, and it connects the rotor with the mechanical load. That means it rotates whenever the rotor starts rotating. Here we have the casing. The casing contains all of the components of the induction motor. Also, the casing helps for the ventilation of the parts inside the induction motor, especially the rotor, to help to reduce the heat and temperature. Also, here we have the bearings. The bearings are connected to the end of the shaft. The bearings help to reduce or minimize the friction between the shaft and the casings, and that gives us more efficiency. And also, an important part of the induction motor is behind here. We have a fan. This fan is directly connected to the shaft, so it rotates whenever the shaft rotates, and the shaft rotates whenever the rotor rotates. The purpose of this cooling fan is to reduce the heat and the high temperature of the rotor inside. Okay, now let's talk about the principle of operation of the induction motor. Okay, we said before that the operation of the induction motor is based on the electromagnetic induction phenomena. That states that whenever a conductor is placed inside a rotating magnetic field, that specific conductor experiences a force on it. That force, or the direction of that force, depends on the direction of the magnetic field and the direction of the current. So what happens exactly is that when we apply an AC force supply to the stator windings, and a magnetic field is created in the windings of the stator. This magnetic field always changes its polarity. Why? Because the current is alternating always. It's always changes its direction. So when the current changes its direction, the magnetic fields change its polarity and intensity at the same time. We know that the phases and the windings of the stator are placed or shifted from each other by 120 degrees. This position and the changing in the polarities of the magnetic fields of the stators creates what we call a rotating magnetic field. This rotating magnetic field interacts with the rotor and creates an EMF induced in the material of the rotor, and that EMF called the rotor EMF. So how does the rotor rotate? So we said that the stator has or produces a rotating magnetic field. This rotating magnetic field interacts with the rotor and creates some kind of relative motion relation between both of them. This motion relation creates or induces a current inside of the rotor. And as we know, when a current is induced inside any conductor, a magnetic field is created around of it. So when after the current is induced inside of the rotor, a magnetic field and a flux is created around the rotor itself. And now we have two magnetic fields and two fluxes, one for the stator and the other for the rotor. These two magnetic fields or fluxes interact with each other, and at one end they cancel each other, and at the other end we have a very high density of flux at the other end. This high density of flux tends to move to the other side to create some kind of balance of density. This what creates or produces a torque that is at the same direction of the direction of the rotating magnetic field. So, in a simple way, the high flux at one end tries to push the conductor to the other end with the low flux density to create some type of balance, and the rotor starts rotating. So, as we said before, the torque is produced due to the interaction that goes between the two fluxes that created by the two magnetic fields from the rotating magnetic field of the stator and the magnetic field induced in the rotor. And as you know, the torque is a rotational force that allows the rotor to rotate or help it to rotate, and as we see, it depends on the fluxes or the two fluxes that interact with each other, and also it clearly depends on the armature current that produces the magnetic field of the rotor and then the flux of the rotor itself. So, as we see from this formula, the formula of the torque of the induction motor, it equals the armature current times the flux and times the geometry constant. The geometry constant equals P times Z divided by 2 by A. P is the number of poles and Z is the impedance, and here we have A, that is the number of parallel paths. A starting torque is the torque that is produced instantly at the beginning of the rotation of the rotor. Once the rotor starts rotating, the shaft directly rotates because we said it's connected to the rotor directly, and the torque starts accelerating, and the shaft is starting to accelerating too. The shaft torque acceleration is not in the same speed of the rotor torque acceleration. Once the shaft torque acceleration reaches the same speed of the rotor torque acceleration, it becomes constant and stops accelerating. So now we are going to talk about the slip in the induction motor. So what is the synchronous speed? The synchronous speed is the speed of the rotating field at the stator. The synchronous speed is always constant, and it depends on the frequency and the number of poles. And as you see from this formula, the synchronous speed equals the frequency times 120 divided by the number of poles. And if we know the number of poles and also the frequency that we are using, we are going to calculate the synchronous speed easily. Now let's talk about the slip. As we said, the synchronous speed is always constant, and the rotating magnetic field created at the stator creates a magnetic field in the rotor, and the interaction between the two magnetic fields and its fluxes lets or makes a torque that lets the rotor rotating. So now we are going to talk about the speed of the rotor, the rotation speed of the rotor. We have to know that the rotation speed of the rotor is always less than the rotating magnetic field at the stator. And that is the definition of slip. The slip is a relation between the speed of the rotating magnetic field at the stator and the speed of the rotor. Whenever the speed of the rotor is less than the speed of the rotating magnetic field, or what we can call the synchronous speed, that means that the lines of the rotating magnetic field will always be cutting the material of the rotor, which means that there will be always magnetic fields created and currents induced and torque produced always, which means the motor will keep on rotating while the speed of its rotor is always less than the speed of the synchronous speed or the rotating magnetic field. From this formula, we see that the slip equals the difference between the synchronous speed and the rotor speed divided by the synchronous speed. So, at the stationary situation before the rotor starts rotating, that means the speed of the rotor is 0, and that means the slip is equal to 1. So when the slip is equals to 1, that means the rotor is not rotating. And if the speed of the rotor somehow reaches the speed of the synchronous speed, that means the slip equals 0, and at this situation it's impossible that the rotor will ever rotate. Why? Because when the two speeds are the same, that means the magnetic field, the lines of the both magnetic fields will be parallel to each other. That means they will never be cutting each other. That means there will be no magnetic fields induced or current induced in the rotor, which means there will be no torque produced. At the same, that means the rotor will stop rotating at this case. Going to talk about how to control the speed of the induction motor. Okay, before we start, we should give a look at these equations that most of them we already know. These equations will help us to understand how we are going to control the speed of the induction motor. From this equation, we can say that we can control the rotational speed of the magnetic field by changing the frequency or changing the number of poles. So the first thing, or the first method to change or to control the speed of the induction motor is by changing the number of poles. That's the first method. The second method is by changing the frequency. But with the frequency, there is something that we should focus on, and that thing is related to the flux itself. Because when changing the frequency, we also are changing the flux. Increasing the frequency will decrease the flux. Decreasing the frequency will increase the flux, the magnetic flux. And that is something that we do not want to happen. So what are we going to do? From this relation, this equation of the flux, we see that the flux equals the supply voltage divided by 4.44 times the constant and the frequency. So what we are going to do exactly is whenever we change the frequency by decreasing or increasing, we are going to change the supply voltage with the opposite. If we decrease the frequency, we are going to increase the voltage. And if we increase the frequency, we are going to decrease the voltage to remain this flux constant, and that is something very important to do. So this method is called the voltage frequency method to control the speed of the induction motor. Another method to control the speed of the induction motor is by changing the amount of the supply voltage. We know from the relation of the torque and the supply voltage that they are proportional to each other. So by changing the supply voltage, by increasing it or by decreasing it, we also increase or decrease the torque, and this leads to a change in the speed of the rotor. But there's something that we have to pay attention to, and it's about the torque itself. For supplying the load, we should give a constant torque to the load. So what happens here is we are going to keep this torque constant even after decreasing or even after increasing the supply voltage. How that happens? By increasing or changing in the slip itself. From this relation, we see that the torque is proportional to the supply voltage times the slip. So if we are wanting to, if you want to increase the voltage to change the rotor speed, we must increase the slip to remain the torque constant for the load or for supplying the same load itself. This method is only for small applications and it doesn't work for high torque or high power applications. As we see here, increasing in the slip will lead to a decrease in the speed of the rotor. And now we are going to talk about the starting methods of the induction motor. We have four main starting methods, four different starting methods. The first one is the direct online starting method. The second is the variable resistant starting method, and the third is the auto transformer, and the last but not the least is the star delta starting method. The most famous method is the direct online starting method. Nearly most of the motors around the world are using this method. In this method, it's the most simple method and the most cheap method, and nearly most of the motors around the world are working with this starting method, the direct online method. In this method, the direction of the rotating magnetic field can be reversed by changing the polarities of the phases at the stator. Another way is also by easily it can happen by changing the places of any two wires only. Doing that will reverse the direction of the rotation of the rotating magnetic field, and then the direction of the rotation of the motor in general will also be reversed. Now we are going to talk about how to reverse the direction of the rotation of the induction motor. To reverse the direction of rotation of the induction motor, we have to reverse the direction of the magnetic field itself. Now let's talk about the power factor. We know that the power factor is the angle between the current and the voltage. But also there's another relation for the power factor, as we see, as the power factor is the relation between the active power to the apparent power. Induction motors, as we mentioned before, most of the induction motors have a high power factor that goes around from 0.8 to 0.9 at full load condition. In induction motors, the power factor is always lagging. That's because of the windings that lays in the stator. The windings has its own resistance and inductance, so the voltage will always be leading the current, which makes the power factors always lagging. The efficiency is defined as the ratio between the output mechanical energy to the electrical input energy. Squirrel cage motors have higher efficiency more than the slip ring motors. Higher speed motors are more efficient than the lower speed motors too. Efficiency is a function of temperature too. That's why the enclosed fan-cooled motors have a higher efficiency than the protected water-driven motors. Efficiency is defined by its losses. That's why it's important to know which losses you are dealing in that specific motor. There are two types of losses. One is the fixed losses that is independent of the load, that we can test at the no load condition, and there are the variable losses that increase and change with the change of the load. The fixed losses includes the core losses such as the eddy, current, and hysteresis loop losses, and also the friction losses that includes the friction between the bearings and the shaft and the casing, and also the windage losses that happens when the air interacts with the rotational part when it rotates. The variable losses are the losses that are related to the loads directly, and we can also call it the cover losses of the both stator and rotor. Whenever the current increase in the resistance in the stator or at the rotor, the